12 m squared k squared divided by 2m squared. And this 16 minus 12, that will give me 4k squared m squared, square root of that, then I'll get plus minus 2km divided by 2m squared. So eventually your omega squared will be equal to 4km plus 2km, that's 6km divided by 2m squared, that's 3k over m. Or the other omega squared will be equal to 4km minus 2km divided by 2m squared. That will be k over m. So eventually this is squared, so we have to square root it. So your omega equal to square root 3k over m, or the other omega is equal to square root k over m. So you can see that you have two natural frequencies now, as what a two-degree of freedom system should give you. Particularly, this natural frequency and that natural frequency, could you see which one is a smaller one, the right or the left one? Which has a smaller value? The right one has a smaller value, so it is the fundamental frequency, I call it omega 1. The other one is a higher one, that's your next frequency, that's your omega 2. So these are the natural frequencies of the system. In the free vibration, the system will oscillate with either one of them. How do we know which one will it oscillate? Later on, I'll let you see. So part 3, it asks you to find out what's the normal modes. So normal modes in mathematics is called the characteristic equation. So I'm not sure if you've heard of that before. I think you should have in your mathematics. That's why you learn about that. So sometimes also called, sometimes also known that it characterizes the mode of vibration, or sometimes it's called your natural mode or your mode shape. So just different ways of saying. You get to hear this mode of vibration a lot later on in your modules when you talk about your aircraft structures. So equation 5, if you look up, equation 5 has 2 equations and 3 unknowns. It is better if I let you see that equation 5. Equation 5 over here. 2 equations, this and that equation. 3 unknowns. Which one are the unknowns? Omega, A1, and A2. These are the 3 unknowns. So 2 equations, 3 unknowns, which are your omega, A1, and A2. That means this is an indeterminate equation. Cannot be determined. 2 equations but 3 unknowns. Cannot be determined, so it's called indeterminate equations. But it is actually possible to solve for not all these unknowns, but for ratios that we call the amplitude ratio. Amplitude ratio of A1 over A2. So if some of you were wondering, why must it be A1 over A2? Can it be A2 over A1? Yeah, it's possible. If desired, yeah, you can solve for A2 over A1. But I'm going to show you A1 over A2. So if you look back from equation 3, that A1 over A2, we can formulate that. That will be equal to K over 2K minus M, 3K over M. So how do I get that? Because I solve this at the condition of omega 2. So this part over here is actually your omega. Right? If you look back at equation 2, and I'm substituting it with omega 2. So someone was asking, wow, can I substitute with omega 1? Yes, you can, because I'm going to formulate the other one. So let me complete this one first. This M and M, we cancel out K over 2K minus 3K. So this is equal to minus 1. So from your equation 4, I'm going to use the same kind of amplitude ratio. I'm going to fill it in with omega 1. So omega 1 was what we saw before over here. Because this one here is supposed to be omega squared, right? So that one minus 2k minus m omega squared, so it becomes m over k, and then divide by minus k. So again, m and m could cancel. So minus 2k plus k divided by minus k. So I get 1. So these are the amplitude ratio. Actually, what does it mean? This one, 1, it means the first mode of vibration. And this one over here is your second mode of vibration. What are all these first modes, second modes of vibration? So these are called normal modes of the system. So how do we understand that? I'll take one by one. Let's take this one first. Case 1. When both masses M are displaced by the same amount, in the same direction. That means A1 equal to A2. So that leads to your amplitude ratio, A1 over A2 is equal to 1. In this case, we call it the free vibration will be at omega 1. That means the masses are in phase. This part here. If it's equal to 1 or the amplitude ratio, that means the masses are in phase. 2, when both masses M are displaced, in the opposite direction. By the same amount. In that case, that means your A1 is equal to minus A2. That leads to your amplitude ratio, A1 over A2 is equal to minus 1. What that means is that your free vibration will be at omega 2, which means your masses are out of phase. So in order to put that into perspective, so I have this setup over here. Two springs that I connected, and I'm going to show you what these are the first case. Two springs. I'm using a hook so that it allows it to like flex about freely. So that first move is going to look something like this here. The top spring, when it extends, the bottom spring also extends. This is the first mode of vibration. Hope you can see it. So the second mode of vibration says that when this is moving up, the other spring is moving down. And this spring is moving down, the other spring is moving up. So that second mode of vibration is going to look something like that, where this cupboard over here is going to stay stationary. So this now was first mode. Now the second mode is going to look something like that. Essentially, the cupboard is kind of like not really moving much. I know it moves. I can't produce that. But you kind of get the idea that when it extends, the other one extends as well. When it's coming back, the other one comes back. So this is your second move. So what I want you to notice is that, look at my hand, that frequency. First mode, this one, this frequency. And then the second mode. That one. Which one has a higher frequency? The second one. So just like that theory, the first one, omega 1 is at a lower frequency, square root 0. The second one, square root 3 is at higher frequency. So my input over here is the one that's giving it that resonance frequency. That's why it can resonate. This one has a first mode, and that one has a second mode. So we're going to invite somebody to try to do that second mode. So try that first mode.
Desmond, you want to buy commando car detail or not? Commando car detail.
Everyone see the one? Yeah, this is the first mode. Now try the second mode. Try that second mode. This cupboard here is supposed to be that it doesn't move. It's going to be at a high frequency. Okay. So what you're saying is actually somewhere in between. You have that first mode and then the second mode. Yep. And then somewhere in between where you have the mixture. Right? So that mixture that is for part 3. For other E1 over E2 values, right? They are not -1 or 1. This free vibration consists of motions at both frequencies, or a combination of those frequencies. So that's that. I'm going to introduce, so you have this case as a free vibration, that is where there's no damping. But you can have a no damping case where I can introduce right up here that sketch again. Okay. I'm gonna copy that one. Copy. I know you can't do that. No problem. Okay. What I want to do is to introduce you your external force. Okay, so a little bit more complicated. So you'll be using the same principle. So essentially, you'll get back the equation that look very similar. So instead of having it equated to 0, so this one F1, this one is F2. You have external force coming into the system. So eventually you have, maybe I'll call this M1, M2 as well. So you have M1 x dot dot 1 plus K1 plus K2. So I'm not going to formulate that. I'm just going to say that this one is equal to M1, right? Considering your left-hand side mass. So for your right-hand side mass, that is M2 x dot dot 2 plus K2 plus K3 x2 minus K2 x1 equal to F2. So it's no longer equal to 0 because that's external force that's coming in. So once we have that in the matrix form, we can formulate that. So you have this M1 and M2. Which is M1 here, 0, 0 here, M2, multiplied by your x dot dot 1, x dot dot 2. This one plus the matrix over here, that is K1 plus K2 minus K2, minus K2, K2 plus K3. Whole thing multiplied by x1, x2. And then this one here, it would not be equal to 0 because you have the external force. So F1 and F2 both. This form here has a basic form. It can be written as M x dot dot tilde plus this whole thing here is K, and then this one is X tilde equal to M tilde. If you are wondering what are all those symbols, so this M is called your mass matrix. This K over there is called your stiffness matrix. And your x dot dot tilde, your x tilde, and your f tilde, they are the acceleration, displacement, and force, not matrix, but vectors. Okay, this matrix is a 2 by 2 matrix. It is a